In my last video, I talked about how to find if two nodes are connected. The program used a basic algorithm which is called quick find. In order to answer the question, all we need to do is look up a hash map which takes constant time. However, constructing this hash map takes n multiply m, and so it's quadratic. If we have a large set of data, it will be too slow during the hash map constructing. The reason it is slow because for each friend pair, we have to iterate through the whole name list in order to just update a few value. This is where we can improve. So instead of go through the whole name list and update the hash map value, we can store the relationship into a tree. So for say John and Ben is connected, we can set John as a root and Ben as a branch. So point Ben to John. The same Miller point to John, and the John became a root of a tree with two branches. One branch is Ben, another branch is Miller. Later, if we want to merge John tree to Yaohai tree, we only have to point Yaohai as a branch to John as a root. Then we get a bigger tree with John as a root. So each time, in order to merge two trees, we don't have to iterate through the whole name list. We just have to traverse two trees and update two records. And that is where the time saving came from. Actually, this one is a linear time, but we can improve it to log n. So let's just do that. In order to keep a tree, we need another collection. We need a private static list. So Java have many implementations of list interface. Array list is general purpose and it's resizable. You can use your own implementation. So the IDs is store index. The value in that index is pointed to the index of its parent node. That's how we build a tree with a list. Okay, they arrange the relationship between the parent index and the child index. So once we have the IDs, we need to initialize. So here we can say IDs at index I, value I. So at the beginning, each index only points to itself. They don't have parents. They are the root of its own. But when we do the union, we just have to link the root. So let's write a helper function called root. It given the index of a leaf, we should return its root. So how we do that? Where IDs get I not equal itself, then we need to keep looking up. I equal IDs get, and at the end we return the root. Okay, once we have this root here, our job became simple. Let's first do the trim, and let's find int root1 equal root v, and we can do the same thing. root 2 finds the corresponding root of name 2. Once we have those two roots, we can link them. The way of linking them is set the value of one index to its parent index. Okay, in this case, we set root 1's value to root 2. That means we merge the two trees. Root 1 no longer is a root. Now it points to root 2. Root 2 became the root of the bigger tree. And root 1 no longer is a tree. Now it's a branch. No longer is a root. Now it's a branch. Okay. When we try to call is connected, what we have to do is we just have to get those two roots and return if they are the same. As we can see, the union function is the cost of the union is traversal a tree, so it's a subset of the name list. The performance is link n. Again, when you're trying to tell if they are the same, the cost is also traversal a tree instead of the whole list. Again, it's link n. In average, I should say in average. But if the tree is really tall, it degenerates into a linked list and the performance degenerated to n. So we don't want a tall tree, we want a shorter tree. So we need to balance this tree. The way to balance is we only want to attach the smaller tree to bigger tree instead of randomly merge trees. So in order to know which tree is shorter, which tree is larger, we need another map to remember the size of the trees. So the first one is an integer of the root. The next one is a count, and we want the size. And since we use a HashMap, we can lazily initialize. Say in the union, we can say int size 1 equal size compute if absent. So root 1, if this is the first time I saw you, I just initialize you as 1. So this is oh, I cannot reuse it. So let's say key. And again, here is size 2. Then I can compare if size 1 bubble e2 equals size 2. That means tree 1 wins. We want to set tree 2 as a branch. So we want to set tree 2 as a branch of tree 1. Otherwise, we do the opposite. Okay, because this time tree 2 is a larger one. Okay, and more than that, we need to update the size. Let's put, in this case, root 1 is the larger one, so it wins. And we need to update the size. Size get plus size get and root 1 and root 2. Here we do the same, except this time we update the bigger tree, the winning tree's size. And this effort is balanced. There's one more thing we can improve here. If a node is not a root, that means it's a branch. We can point the current node to its grandparent, so make the tree shorter. So edit, set, okay, set I equal edit get I. So each time we iterate through, the tree became shorter, and program runs faster. This is called path compression. Just another trick to make our algorithm more efficient. Let's run the program. Here, let's say John and kids. It's worse. And let's print out the tree. Tree is the IDs. Okay. Here, let's say John and Eva. Let's see. Here is a 0 pointer itself. This is a tree root. Index 1 point to 0, index 3 point to 0. So this is a tree, which corresponding to mirror John and I think Ben and Eva. John, Ben, and there is another point to 0, which is Eva. And for Yohai and Wushi, I believe those two are the other tree. And by create a tree instead of update the HashMap value, we save a lot of traversal. We just traverse through the tree from the branch to the root, which is a subset of the whole list. And we save a lot of computation, and that make our program faster. Just by the way, if we can write a program to reading a lot of data, so here make names, have a buffer writer which write into those. Here I have a small set. However, I can set the value larger and randomly link to them, later read in. So I will put this code into the link. Quick union. It's called quick union.